Hi, this is second part of lecture 14. And what I want to do in the second part is I want to go over a few problems that are kind of simple problems that have to do with the momentum and with the conservation of momentum. So I will start with problem 14.1. This is on slide number 7. In 14.1, you have a tennis ball, and this tennis ball bounces off a floor like so. Okay. Now, the velocity of this tennis ball, its speed is 10 meters per second when it bounces down, and it's 10 meters per second when it bounces off. We know that the angle is 30 degrees, so this angle is 30 degrees, and this angle is also 30 degrees. And there are two questions. Question number one is what happens to the energy of the tennis ball? And question number two is what happens to the momentum of the tennis ball? Let's start with question number one. The energy. This question is relatively easy. You know that the energy is mv squared over 2. And if you look at this tennis ball, when it bounces, its mass doesn't change, the speed doesn't change, so the energy doesn't change. That's the answer to part A. Energy doesn't change. Now, part B is kind of a bit more complicated. What happens to the momentum? You have to remember that momentum is a vector. It has both magnitude and direction. So even though the speed doesn't change, direction of the velocity changes, so momentum also changes. So to find the change in momentum, what we need to find our initial momentum and our final momentum. So let's assume that this tennis ball has a unit weight. Let's say it weighs 1 kilo, although it's a bit too much for a tennis ball, but for simplicity, let's say it's 1 kilo. Then momentum is mass times velocity. So mass is 1. I will be skipping mass. Let's look at the velocity. I have two axes. This is my x-axis. This is my y-axis. And when I'm computing my initial and final momenta, I have to now compute both x and y components. So let's start with the initial momentum. I have momentum initial x, momentum initial y. So mass is 1. I need to find the velocity. Yeah. Okay, so let's look at this velocity. This velocity is pointing this way. And to project this velocity on x and y, I will need to use a little bit of trigonometry. So I'm looking at the triangles. This angle is 30 degrees. Then this angle must be 30 degrees. So this will be my x projection. This will be my y projection. So you see that to project on x, I need to project on the opposite side of the angle. And to project on y, I need to project on the adjacent side of the angle. So this means that my p initial x is 10 times the cosine of 30 degrees, and my p initial x is 10 times the sine of 30 degrees because it's the opposite side, and p initial y is 10 times the cosine of 30 degrees. Now I have to be a bit careful with the signs. So if you look at this velocity is pointing kind of down and to the right. So my x projection is positive, but my y projection is negative because the velocity is pointing down with respect to the y-axis. So I need to put a minus sign here. Okay, let's do exactly the same thing with the final momentum now. I will have p final x, p final y. I will do exactly the same thing. I will try to do my projections. So this is a 30-degree angle. This is my x projection. This is my y projection. And things are going to be almost exactly the same. My x projection will be 10 times the sine of 30 degrees, and my y projection will be 10 times the cosine of 30 degrees. The only difference is that now my velocity is pointing up with respect to the y-axis, so I don't have a minus sign here, I have a plus sign here. Okay, so we're done with initial momentum and the final momentum, and now the change in momentum is momentum final minus momentum initial. And if you look at these expressions, you will see that in x direction my momentum didn't really change. So my change in the x direction is 0, and in the y direction I have 10 times the cosine of 30 degrees minus negative 10 times the cosine of 30 degrees. That's 20 times the cosine of 30 degrees. So that's my change in momentum. No change in x direction, and this much change in the y direction. And now, if something is not clear here, if you have additional questions, I will have a Zoom session on Monday and on Wednesday. Please join in, and I will be happy to help you out more. Okay, let's move to problem 14.2. This is slide number 8. And in this problem, we have a space shuttle. So there is the space shuttle that's flying with 600 meters per second. And then the space shuttle ejects, a cargo. So now it's in two parts. The remains of the space shuttle, they continue moving with 1500 meters per second. And the speed of the velocity of the cargo is unknown. So this we don't know. So on this picture, the left-hand side is what happened before the ejection, and the right-hand side is what happened after the ejection. They also tell you that the cargo is 20% of total mass, so it's 0.2 times m, and the shuttle, the remaining part of the shuttle is then obviously 80% of the mass, it's 0.8 times m. Okay, so let's think, the question is to find the velocity of the cargo. Now let's think about how we can solve this problem. You see, so before and after this process, what happened in between is kind of complicated, right? This space shuttle ejected cargo, but I don't really know what kind of forces were in action, how big those forces were, for how long they acted. So it would be impossible in this case to solve this problem with conventional means, like writing down Newton's laws and solving for acceleration, and then integrating acceleration to find velocity. So that would be kind of difficult to do. But since this is a space shuttle in space, and it's isolated from any external influence, we can even though we don't know anything about the forces, we can still use conservation of momentum. So that's what I'm going to do. Conservation of momentum means that momentum before the cargo was ejected is equal to the momentum after the cargo was ejected. Now, on my slides, I call this quote-unquote explosion. I call this explosion because we had one body, and this one body is now, separated into two bodies. So, it's not. It may not really be an explosion in a chemical sense, but we will call this kind of processes explosions from now on. Okay, so let's see. What's my momentum before the ejection? My momentum before the ejection is mass of the spacecraft times 600. And what's my momentum after the ejection? After the ejection, I have two bodies. One of them has momentum, which is 0.2 times m times v, where v is unknown. And the second body has a momentum, which is 0.8 times m times 1500. Okay. So in this case, I don't really have to worry about x and y axes because everything is moving on a straight line. Okay, so first of all, you can immediately see that mass cancels out because it's, every single term in this equation has mass, so we can just cancel it out. And then you can easily solve this equation. The solution is V is equal to, let me see, 600 minus 0.8 times 1500 divided by 0.2. Okay, so that's your velocity. I'm not gonna, solve this completely. You can get the number, and whatever is the number that you get, that will be the velocity of cargo in meters per second after the ejection. And you should also be mindful of the signs. If you get a plus sign for this velocity, this means that the cargo continues moving in the same direction. But if you get a minus sign, this means that cargo is now moving in the opposite direction. So that's it. That's how we use conservation of momentum to solve this kind of explosion problems. And I think you can, you appreciate the fact that even though we knew very little about the process itself, we were still able to solve it by using conservation of momentum. So that's basically the main strength of the main advantage of having conservation of momentum in our tool set. Okay, let's move to the next problem. This is problem 14.3. That's slide number 9. And in this problem, what I have is I have a coconut. So there is this coconut here, which is initially stationary. But then something happens to the coconut and it gets separated. It explodes into 3 separate parts, 3 separate and equal parts. There is this part A, there is this part B, and there is this part C. So part A, part of B, part C. All these parts are now moving. So part A has velocity of 2 meters per second. Part B has a velocity of, what's the velocity? A velocity of 5 meters per second. And the velocity of part C is unknown. And this is what we have to find. We know some angles. We know that this angle between part A and part C is 100 degrees. And we know that the angle between part B and part C is 130 degrees. Okay, so how do we solve this problem? Again, we don't know anything about the forces. There were some explosion forces involved. But what we know is, this is before, this is after. we know that this coconut was isolated, nothing from outside was influencing it, so we can use the conservation of momentum. I can write momentum before is equal to the momentum after. So what was my momentum before? Before the explosion, this coconut was just sitting there. My momentum was 0. Momentum before is 0. What about momentum after? After the explosion, I have 3 parts. I have mass times velocity A plus mass times velocity B plus mass times velocity C. So I'm using the same m here because these parts are have equal size and equal mass. And as you see, m actually cancels out. We have 0 on one side, so m cancels out. Now it's very important to keep these arrows on top because velocity is a vector. So these velocities, because momentum is conserved, must add up to 0 in a vector sense. So since I have vectors and since these vectors are not aligned, I will have to do some projections. Let me think about what kind of projections I want to make. So I need to decide which way do I point my x and y axis. Okay, so I need some axis, and what I will do is, since velocity of c is what I'm interested in, I will put one axis, let's say x-axis, in the direction of c. Okay, so I will put my x-axis like this, so that I don't have to project c. And then my y-axis will be pointing like this. So this is my x, this is my y. So it's velocity c that I'm looking for, and velocity c, now that I made this choice, only has x component. So I only have to look at the x component of this. Really, I'm not really interested in the y component. So let's write down this equation. For the x axis, I have 0 is equal to the x projection of v a plus the x projection of vb plus the x projection of vc. So now to find these projections, I will have to do a bit of trig. Let's start with velocity a. Actually, I don't need to do any trig because they tell me what the angles are. Velocity A makes a 100-degree angle with the x-axis. Velocity B makes 130 degrees with respect to the x-axis. So I will just write 0 is equal to 2 times the cosine of 100 degrees plus 5 times the cosine of 130 degrees plus VC is equal to 0. And from here, it's, this is a very simple equation to solve for VC. VC is equal to negative 2 times the cosine of 100 degrees minus 5 times the cosine of 130 degrees. Okay, this problem is solved. And again, the point, the main point here to pay attention to is that, again, we knew nothing about the forces involved, but the conservation of momentum helped us to solve this problem anyway. Okay, now let's move to problem number 14.4. This is on slide number 10. And in this problem, we have a projectile. Right, let me draw this here. yeah, I have a projectile, some sort of a bullet. This projectile hits a box, gets embedded in the box, and then the box will start moving, of course, because there is no friction. They tell us there is no friction or little friction between the box and the surface. Now, what do we know? We know that the bullet has a mass of 10 grams. That's 0.01 kilograms. We know that bullet is moving with the speed of 200 meters per second. And we know that the mass of this box is 2 kilos. Okay, so again, when this bullet hits the box, there are very complicated forces involved that I don't really know. But since the box and the bullet are isolated and there are no external forces, I can write down that the momentum before they got stuck together is equal to the momentum after they were stuck together. Now, what's the momentum before? Before all this happens, it's only the bullet that's moving, so it's just the bullet. So my momentum is m times v. This is 0.01 times 200. Now, what about after the collision happens? After the collision happens, I have a bullet and the box moving together. Their combined mass is 2.01, and their velocity is unknown. Velocity is v. I have a motion in 1D, one direction, so there is no reason to project anything. And this equation, again, is very simple to solve. V is equal to 0.01 times 200 divided by 2.01. And this is, now let's actually compute this number. This is 200 times 0.01, which is 2 divided by 2.01. And this is, almost, to very high precision, it's 1 meters per second. So you can see how the initial velocity was very high, but the final velocity is kind of low. And that's understandable, because in the beginning you had very little mass, and now that momentum has to be redistributed to a much, much larger mass. So the velocity drops. Okay, so that's all I had for you today. I hope at least some of this was helpful and was something that you understood. Even though we're doing this remotely. And just to remind you, on Monday and on Wednesday during regular class hours, which is 12:30 to 2:30 Central Time, I will have a Zoom room open. You can join. It's not mandatory. You don't have to, but you can join if you want to, and you can ask me any questions that you have about quiz or about homework or anything else. Okay, thank you, and see you on virtually on Monday.